important to study here. Before that, I would like to explain this electronic configuration. Electronic configuration. And this configuration also depends on the strong field ligand and as well as weak field ligand. Okay. So first, before that, just do the electronic configuration. If we have number of electron, I'm going to write here. If you are going to have only one electron, then two electron, 3, 4, 5, 6, 7, 8. We will do up to 10. It's very important. Now, here SFL, if it is a strong field ligand, you still remember, I think, that in a strong field ligand, pairing will take place.
Yes.
Is that clear?
Yeah.
So here that means electrons will pair up. Electrons will pair up. And then you can see if you are going to do the electronic configuration in terms of T2G and EZ, I'm going to write T2G1 and EZ0. Then I'm going to write T2G2 and EZ0. Again, I'm going to write T2G3 and EZ0. Is that clear? First, the lower energy level filled 1, 2, 3. Because in lower energy level, we had 3 orbitals, right?
Yeah.
Now, again, if you are going to fill the fourth electron in EZ, it will be wrong for SFL, a strong field ligand, because in a strong field ligand, the electrons pair up. So again, the fourth ligand will come to this T2G4, EZ0. Again, T2G5, EZ0. Then T2G6, EZ0. T2G7, yes, up to this. Is that clear?
Okay. Yeah.
Are you getting my point?
Yes.
Now, after 7, since all the T2G are filled, now we can go for T2G6, EZ1, and T2G7, T2G6, EZ2. Are you getting my point?
Yes.
Because not more than 7 electrons will can go.
Yeah.
Then again, T2G6, EZ3, and then we can write T2G6, EZ4, and this is 9th electron and this is 10th electron. Yes or no?
Yeah. Okay.
So there are questions that can be that is asked directly about this in the electronic configuration in terms of T2G and EZ. Now, if you are going to do for WFL, weak electrons won't pair up, right? Electrons won't pair up. So what you need to do, it's very easy. T2G1 easy. First, it will go lower energy level. In lower energy level, then T2G2 easy, and then T2G3 easy. Electrons won't pair it. That means T2G and 3, and then EZ1, and then T2G3 EZ2, and then it becomes T2G4 comes to the lower energy level again, and EZ2, and then T2G5, and then EZ2, and then T2G6 EZ2, and then T2G6, since it is filled completely, then go to the 3, and then T2G6 EZ4. This is how we are going to do configuration in terms of T2G and EZ. Are you getting my point?
Yeah, I got it. Yes. Yeah.
So this is the configuration which is very important. Now we are going to see for a spectrochemical series on which we can easily tell that which one is a strong field ligand and which one is weak field ligand.
Okay.
Okay. So can I change the slide?
Wait, last few.
Yeah.
Yeah, done. Okay.
Done. Very good.
Yeah.
Now see, if you are going to have a question, I'm going to write a question for you, then I will move ahead for a spectrochemical series, which is correct EC that represents electronic configuration of central atom in K4FeCN whole 6. As I already told you, what is CN? Is it weak or strong?
Yeah, strong. Yeah.
Yeah.
Yeah, is it T2G6 EG0?
E2G6
6,
EZ0.
yeah.
Very good.
Yeah.
So it's very
Okay.
easy. As you can see, this is I think Fe what? Fe plus 2, right?
Yeah, 2, yes.
So if you are going to do the electronic configuration, so always try to do the electronic configuration of neutral atom and then go for the, as we know for Fe, it will be argon 4s2 3d6, right? So for
Yeah,
Fe
yeah.
plus 2, it will be 4s0 3d6, right?
Yes,
So
yes,
for
yes.
3d6, since it is a strong field ligand, it will be paired up. So it will be T2G6 and AG0. Very good.
Okay.
Now see about the spectrochemical series. Spectrochemical series. It's very easy. A spectrochemical series is just like a series on, if you have studied electrochemical series in electrochemistry. So it's just like that. So
Okay.
spectrochemicals, so the weakest ligand is I minus, then comes the Br minus, then isocyanide, SCN minus, then Cl minus, then S minus 2, then F minus. These are all weak field ligand. Then OH minus, hydroxide ion, and then C2O4 minus 2, and then H2O. And from after this H2O, we consider it the what we call a strong ligand, NCS minus, and then comes EDTA4 minus, EDTA4 minus, and then comes your NH3, and then comes your En, and then comes Cn minus, and then comes CO, the strongest ligand. So from here, you are going to learn all these are strong,
Okay.
a strong ligand. Okay. So
Okay.
this is, I think, very easy to understand, right?
Yeah, yeah, yeah.
Okay. Can I change the slide?
Yes, yeah.
Okay. Now see, we are going to do the this is splitting for tetrahedral as well. So in tetrahedral, we say T2 or E only. Okay. So this is your d orbital, degenerate d orbital that are equal in energy, and then it will go for bonding, and then it will be split into two parts as same. This will have two part, that is dx. This has basically three parts in it. These are opposite. So this will be dxy, dyz, and dxz, and the lower part will be basically dx square minus y square and dz square. And this is your E, and this is your T2, and this is the barycenter that we just studied, and this is your 2 by 5 delta T, and this is your 3 by 5 delta T. This is your 3 by 5 delta T. Please do write it. It's very important.
Yeah, yeah. Wait, why here delta T and not delta naught? Like,
T stand for basically tetrahedral, no, and delta naught. O stand for octahedral.
okay, okay.
It's very easy.
Yeah, yes, done.
Wait a minute. Let me take some questions. So after this chapter, which chapter we are going to learn?
Yeah, P block, right?
P block. Okay. Okay. Wait a minute. I need to give you some questions. Are you solving the assignments and all? Okay, I need to.
Yeah, yes, yeah.
Okay, very good. So low spin and high spin. Are you aware of this term in class 11th?
Uh, no, not clear. No, 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 no.
Okay. So see, spin. There is a quantum number that is a spin quantum number. I think you remembered it.
Yes, yeah, I know that.
Principal
Yeah,
quantum number, azimuthal quantum number, and then
yeah,
magnetic quantum number, and then comes the spin quantum number. That says if you are going to do electronic configuration, first you are going to fill it like this: spin up, and
yeah,
this is your spin down. So if I'm asking you, if I'm going to ask you, which one is having high spin, which one is having high spin, this one or this one? As you can see, they will cancel each other. So the spin will be zero here.
oh, okay, okay.
Are you getting my point?
Yeah, yeah,
Clockwise,
yeah,
anti-clockwise, they will cancel each other. But here
yeah,
you
yeah.
can see all the electrons are at spin up. That means the high spin. It is of high spin, right?
Okay, okay. Okay,
So
that's it.
now,
Okay.
yeah, now you can connect it with SFL, a strong field ligand, low spin because they pair up, and weak
Yeah,
field ligand that does not pair up is of high spin. Are
yes,
you
yes.
getting my point?
Yeah,
So
yeah.
in the question, it will be uh, come in form of spin, low spin or high spin, from where you have to confirm yourself that it is of weak field ligand or a strong field ligand, or high spin that means unpaired, and low spin that means paired. Are you getting my point?
Okay. Yeah, yeah.
So wait a minute. Mm, I need to give you a very good question on this. Where is the question? Okay. Crystal field stabilization energy for high spin D4 Octahedral complex is, I'm going to give you option as well, minus 1.8 delta naught, that represents octahedral it is, and this minus 1.6 delta naught plus P, and then C minus 1 point delta naught, and for D it is minus 0.6 delta naught. Please do attempt it and let.
Okay. Yeah, not getting.
Okay, I'll explain it. It's very easy. Wait a minute.
Yeah.
Okay. So as you know that this is an octahedral complex, right?
Yeah.
So if you're going to do this, delta naught is basically for what we call 3 by 5 delta naught and plus 2 by 5 delta. Can I write it?
Yeah. Yeah.
Now see, I can also write this as 0.6 delta naught and this is 0.4 delta. Now, as you know, this is high spin. That means pairing will take place or not.
No, no pairing. Yeah, weak field.
No pairing. That means basically you are getting three electrons here and three orbitals here and two orbital here. And you have four electrons. That means one, two, three, four. Yes.
Yeah, yeah, yeah.
So in this T2G, sorry, this is T2G or EG?
Easy, right? Yeah, easy.
Easy, easy. How many
Yeah.
electrons do you have? One electron, and one electron will have energy this much. So 0.6 into one electron. Are you getting my point? And this
Oh,
is 0.4. And how many electrons does it have? So it will have basically in negative because it is lower energy level and that is higher energy level. You can replace it by this, and it will have a value for three electrons are there. Three electrons are there. So 3 into 0.4 minus 0.4 and delta naught. So it will have a value 0.6 delta naught and minus 1.6 delta naught, which will have a value minus 0.6 delta naught. So in the lower energy level, we use negative sign, and here in higher energy level, we use positive sign. And in this way, you can easily calculate the value of this crystal field as stabilization energy. This is okay, CFSE.
okay.
Okay, so please do write it. It's very easy and
Yeah.
important. There was a lot of question on this. Let me just check it and I'll give you.
Yeah, done.
Very good. There is also a relation between this octahedral and tetrahedral, and that is tetrahedral the crystal field stabilization energy is equal to 4 by 9 delta naught octahedral. Always remember this.
Okay.
Please do write it.
Yeah, done.
Yes, yes. This is
Yeah,
for
done.
tetra. There is a relation between. Very good. Very good. Okay. Okay. Now let me give you a very good question. Just to wait for a minute. Okay. See, the questions I'm going to give you. This relation is very important. So just make a short notes and keep it there. It's
Yeah.
very important. Which of the following complex compounds will exhibit highest paramagnetic nature. I'm going to give you Z of titanium first. Titanium, that is 22. Chromium, that is 24. Cobalt, that is 27. And zinc, that is 30. And the option is NH3 whole 6 plus 3. CrNH3 whole 6 plus 3. CuNH3 whole 6 plus 3. And D is zinc NH3 whole 6 plus 2. Please do.
Okay. Yeah, B option.
Very good. So it's a B.
Okay.
So I think you can easily do this type of question, right?
Yeah,
Now
one
there
doubt.
is another question which is
Yeah, one doubt
yeah.
I have. While filling the crystal field octahedral complex
Yeah.
in strong field again, will we like use Hund's rule there also? Like for T2G, we'll fill individually, like each
Yeah,
box.
yeah. That is the basic. You are going to fill it singly and then doubly. Are you getting my point? Is this what you asked?
Yeah. So let's say it's T2G3. Then
Yeah.
it won't be two electrons in the first one and one electron there. It will be one
No,
electron
no,
in
no,
each,
no.
right?
Singly filled.
Singly filled in a strong field again.
Yeah,
Okay.
everywhere singly filled. Like if
Okay.
you
Okay.
have a strong field ligand, you know
Yeah.
this is your 3 and this is your 2, and you have only 6 electrons. So what you
Yeah.
are going to do, it's very easy. That is 1, 2, 3, 4, 5, 6. And if
Okay.
you have weak field ligand, that is what you need to do is very simple. So it will be 1, 2, 3, then 4, then 5, then come to this 6, 7 of bow principle, right? Also,
Yeah. Okay. Okay. Yeah.
now there is a question which is also very easy as well as important, and that is basically the crystal field stabilization energy, CFSE, for CuCl6 raised to the power minus 4 is 1800, 18,000 basically,
Okay.
18,000%. The CFSE4. Please do.
Yeah.
Davis,
Yeah.
are you done with this?
No.
Okay, take it. I'm
Okay.
waiting.
Yeah. Is it option D?
B, did you say B?
D. Fourth one.
Okay, it might be correct.
Okay.
So which formula you applied? I think you have applied the formula this that I wrote, right? Delta T is equal to what? 4 by 9 delta naught, right?
No, I didn't. I I just saw that the cobalt in both of them have same electronic configuration. So I thought, oh, both are equal.
Okay, not D. It's not D.
Yeah, it's
So
not D.
basically,
Okay,
you
okay.
know that yeah, delta T is equal to 4 by 9 delta
Yeah,
naught. What is this? This delta naught is CFSE, crystal field stabilization energy for tetrahedral, and this
yeah,
is your CFSE for octahedral, right?
yeah,
So
yeah. Right.
octahedral is given, and we need to calculate the tetrahedral. So you are going to put the value, and you will get your answer 18,000. So it will be cancelled by 2,000, and then you will get 8,000 per
Oh,
centimeter. So these formulas are very, very important.
okay.
Okay.
Yeah, wait. So when can you apply this formula? When the central metal atom is same?
Yeah, almost same. Yeah, it will be same when the basically this
Yeah.
and this are same ligands and
Okay.
central matter atom. Then you can there is a formula for crystal field stabilization energy for octahedral and tetrahedral. Got
Okay.
it?
Okay. Yeah, yeah. Wait, I'm writing. Wait.
Very good.
Yeah, done.
Done. Very good. Wait a minute. There is. Do you know color? Which compound shows color or not?
Yeah, yeah, no.
Which compound can show color or which compound no,
Yeah,
cannot show color?
uh, if it's paramagnetic, it will show color. If it's diamagnetic, it won't.
It won't. So
Okay.
if there will be a question, wait a minute. Not there will be no question on this. First of all, we are going to complete this carbonyl bonding in carbonyl compounds.
Okay.
Bonding in carbonyl compounds. CPDS that represent compounds. Now you can see this carbonyl is basically CO. So basically, only in this type of complex, only carbonyls are present. Carbonyls are present. That means the ligand will be carbonyl, that is CO. Are you getting my point? And
Yeah.
since only one type of ligand is present, it is also known as homolaptic complex or homolaptic coordination compound. Is
Yeah.
that clear?
Yes.
Now there is a very important. Wait a minute. I'll show you the structure. It's very easy and important. Do you know there will be sigma and pi bond as well? So this is your metal carbonyl, and this is the orbital. This is the orbital that I'm going to draw. As you can see, D will have double dumbbell, so it will be like this, and then like this. So as you know that there will be carbonyl that will have triple bond, and there will be orbital free in this way, and O will also have orbital like this. Now see what will happen here. First of all, this carbon will have lone pairs that will donate directly to this, okay, and make a bond that is sigma bond. Formation of sigma bond will take place. Now
Okay.
this metal will be bonding with this that will make pi bond, and again this will have two electron that will make pi bond with this, and this is your pi bond. First of all, you need to take care of this. This is your pi star, that is anti-bonding ABMO. You have studied it in chemical bonding,
Yeah.
anti-bonding molecular orbital, and this will be your basically BMO, that is bonding molecular orbital. And this is the
Yeah.
representation of synergic bond, synergic bonding, synergic bonding. Now see, if you want to see, you know that this carbonyl compounds or complex compound will have oxidation state. The central metal oxidation, the central metal have oxidation state 0. Yes or no?
Yeah, yeah.
It will be also always 0. So NiCO4 will have simple structure. NiCO will have, just let me know the structure, geometry. It will be tetrahedral.
Yeah, yeah.
It will be tetrahedral. So I'm going to write all the possible whatever given in our syllabus, the carbonyl compound. You are going to tell me the what we call geometry.
Okay.
So this will be, I will be asking some more question in this. CO, it's carbon monoxide, not CO cobalt. Okay.
Yeah, yeah.
So what is the geometry here?
Yeah, trigonal bipyramidal.
Bipyramidal. Can you tell me
Yeah.
how many types of bonds are here?
Oh, types of bonds. Okay. Yeah, only sigma bonds, right?
Oh, okay. I'm not talking about sigma bond. All the single bonds are sigma bond, right?
Yeah, yeah. Yeah.
So I'm talking about uh, there are basically these all bonds are equal, right?
Yeah, yeah. Yes.
In tetrahedral, all the bonds are equal. Does this apply to this trigonal bipyramidal? All
No, I
bonds are
think
equal,
axial ones are different from the equatorial, right? Yeah.
axial and equatorial. So that's
Yeah.
what I was asking. Axial,
Okay.
axial, equatorial, 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 and these axial are greater than or lengthier than equatorial, right?
Yes. Yeah.
What will be the bond angle between axial and equatorial?
Uh, yeah. It is 90, right?
90 degrees.
Yeah.
What will be the angle between axial and axial?
Axial 180. Yeah.
And what will be the angle between equatorial equatorial?
120.
One.
Yeah.
Very good. Why axial are lengthier than equatorial?
I don't know.
Okay. See. As you know, this is our, I'm going to take an example of this PCl5 because both have same structure and it's very easy to draw, right? That's why I'm
Yeah.
taking it. Okay. So it is same, the process of trigonal bipyramidal, and you
Yeah.
can see this is the structure. This hybridization is sp2 sp2 sp2.
Yeah.
Okay, and this has a hybridization sp3d. So this will have hybridization. The only I am going to partition this hybridization. The central atom has a hybridization sp3d, and I'm going to do the hybridization for each orbital. You can see this is for sp3, sorry, sp2 sp2, and this is
Yeah.
for pd, and this is also for pd. And as you
Yeah.
know that S character increases, electronegativity increases, right?
Yeah. Yeah. Yeah.
Very good. Now see, what is the problem here? So there is S character, that means it is, this bond is more electronegative. So there will be force of attraction. That's why it slightly shrinks. But there is no
Oh,
S character, so this will be larger. And there is another condition for this also. Apart from this, this is the first reason. You can understand S character is there, so electronegativity difference and it can attract each other, right?
yes. Yes. Yeah.
Another reason is that if this bond will be shorter, there will be force of repulsion.
Okay.
Are you getting my point? Because there are 5 bonds and 3 bonds are like this, so there will be repulsion, and in order to minimize the repulsion, it will go farther from the initial. Okay.
Yeah. 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 Yes.
Very good. So can I change the slide?
Yeah. Yeah.
Okay, one more last question. How many equatorial angle, how many bond between axial and equatorial?
What? What? How many?
How many bonds, sorry, angle, how many
Okay.
angles? Yeah.
Oh, angle between axial and equatorial.
Axial and equatorial. This.
Yeah. 90. Yeah. Yeah.
Yeah, that is 90. But how
Yeah.
many this 90 degree angle present in this compound?
Okay.
How
Like
many
that.
angles? Yeah.
Yeah. 6, right?
Very good.
Yeah.
Mm. Okay. So there are some more examples that we can go for. CR, O, and there will be O as well. There will be O, CO. It's all CO. Okay.
Okay.
And then CO and then CO. Just let me know the geometry.
Yeah. This is octahedral.
Very good. There can be more than one central atom in a complex. Are you getting my point? As you can see, this is Mn and this is CO. I'm going to show you. And this is also CO and this is CO as well as this is CO. And this is also CO. And there is another Mn in which CO is here. CO is here. CO is here and CO is here. So there can be more than two central atoms in a complex.
Okay. Okay.
Mn2 CO whole 10. This is how we are going to represent.
Okay.
So you can see another I'm going to represent. As you know, this is C double bond O. There can be cyclic structure also, and this will be like this C double bond O, and then CO.
Wait, that is cobalt or like?
This is cobalt. This is
Okay. Okay.
this is cobalt. So you know central metal atom or central metal ion. The
Yeah.
central atom will be what metal. Central
Yes.
atom will be metal, and also it is very important. D block element generally do this. There will be some exception. So this is CO2, CO whole 8. So these are some examples that you need to take care of. This is very important.
Okay. Okay.
Okay. So please do write it.
Yeah. Done.
Done. Very good.
Yeah.
Now I'm going to show you question. As you can see, there will be a question like this. I'm going to write a sentence that is Polish girls are ultimate visitors in my restaurant. Do you own restaurant?
Okay. Yeah. Both are fine.
Do you have restaurant? Yes or no?
Like restaurant as in, yeah, near me. Yeah. Yeah.
What I asked, do you own a restaurant? Yes or no?
No. 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 No.
No. So just cut it because we don't have a restaurant, right?
Okay. Yeah.
C for cosmic, C for cosmic, G for gamma rays. This becomes X because we don't have restaurant. So it is X rays. U for
Okay.
ultraviolet, UV, V for visible, that has a range we are going to see. I for infrared, and this is M for microwaves, and this is R for radio waves. Questions can be asked. Arrange them in the name will be given and can be asked which of the following series is correct according to their increasing wavelength or frequency. So whenever you are going from left to right, the lambda will be increasing. Are you getting my point?
Okay. Okay. Yeah.
In class 10th, we have studied about Vibgyor, right? Violet
Yes.
indigo.
Yes.
Can you tell me which one has the highest or longest wavelength, longest
Yeah. Right.
wavelength in
Right.
red? And here stand radio R for radio waves. So it will have the longest wavelength among these. So this is how you are gonna uh, remind yourself if you forgot where the wavelength will increase. So in
Okay.
Vibgyor, we have studied in our childhood that red has the longest wavelength. So here are the radio waves, which has the longest wavelength, and you also have studied it in class 11th. E is equal to wait a minute.
Okay.
You also have studied this. Let me know when you are able to see this screen.
Yeah, able to see. Yeah.
Okay. You also have studied this E is equal to h nu. Nu is frequency, and which is also equal to hc upon lambda.
Yeah.
Nu is basically c upon lambda. So as you can see, lambda increases, nu decreases. So from left to right, nu, that means frequency, decreases, and vice versa, you can say. So whenever there will be a
Okay.
question, so you can do this from this sentence, which is very easy, right?
Yeah. Yeah. Yes. Yes.
And if
Yeah.
there will be any question like which of the following will show color or color compound or not, what you need to do is just calculate the magnetic moment, and magnetic moment will be calculated if you know if you know how many number of electrons are unpaired. So if there is no unpaired electron, that means it will not show the compound will not show color. And if there will be paired electron, that not paired electron in unpaired electron present, then it will show what
Color. Yeah.
color. So please do write it. There is a term that we don't know, that is chelating liquid. Please do let me know when you are done with this.
Yeah. Done. Yes. Yeah.
There is a question, a term that can be asked. Which one of the following is chelating ligand? So the chelating ligand is the ligand which can form a closed ring. So I'm going to just define it and you will get it. No
Okay.
problem. See, so I'm just going to define it. Ligands resulting in resulting in closed closed ring structure, closed ring structure with metal ion are called chelating ligand. Are called chelating ligand. So as for example, you know EN, ethane 1 comma 2 diamine, yes or no?
Yeah.
So as you know, this is your NH2 and this is your CH2, and this is also your CH2 and this is your NH2. And again this is your NH2 and this is your NH2, and again this is your CH2 and this is your CH2. So as you can see, this is forming a closed ring. So that means it is a chelating ligand. CuEn whole twice raised to the power +2.
Okay. Okay. Okay.
If the question will be asked which one of the following is chelating ligand, so this is how you are going to solve the question.
Yes. Yeah.
So can I change the slide?
Wait 1 second.
Yeah, yeah,
Yeah. Okay. Done. Yeah.
very good. Now see, it's very easy. The next topic that we have left in the beginning of this class, that is Werner's theory.
Yeah.
And this is the first theory that was given for coordination compound or complex compound. So this is Werner's theory of coordination compounds. So as you can see, the postulate it has given, it is important to write. So basically in a coordination compound or complex compound, every atom, or we can write each metal ions, possess two types of valencies. Two types of valencies. As we have studied ligand and counter ion. Okay, are you getting my point? So this
Yeah.
is the first theory that is given by Werner, and it the postulate shows that says that each metal ions possess two types of valency. The first one is, I already told you, is a primary valency, and the second one is your secondary valency. Are you getting my point?
Yeah.
This primary valency is ionizable. This primary valency is ionizable. And also this is ionizable and this is non-ionizable. This is non-ionizable. And it is also important to note that this is satisfied, or it depends upon oxidation state of central metal atom. Are you getting my point? This primary
Yeah.
valence is ionizable. That means it is a counter ion, and its number depends on oxidation state of central atom. When we were writing the formula of coordination compound, if you remember, number of the number of counter ion depends on the charge on central atom, right?
Yes.
That's why
Yes.
I
Yeah.
we did see first I wrote K and then see that there is plus three oxidation state. Then I did K2 and for Cl3. Are you getting my point?
Yeah. Yeah.
So this is the concept behind it. Primary valency now is known as basically your what counter ion. Okay,
Okay.
and as you can see, this is your secondary valency, which is non-ionizable, and now it is known as ligands, right?
Okay. Okay. Yeah. Yeah. Yes.
Now it is also important to note that this depends on number of donor atom. Okay,
Yes.
it is formed by basically donor, and then it is also important to note that it represents coordination number. It represents coordination number, right?
Okay. Yeah. Yeah. Yeah.
That ligands, how many bonds they are making, that is the coordination number.
Yes.
And it depends on size and charge on central metal atom. Is that clear? If the atom is larger, that means it will have more d orbital, or there will be a lot of space to take electron. Or if the atom will have more charge, it will be requiring more ligands to satisfy itself.
Yeah. 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 Okay.
Okay.
Yes.
Wait a minute. Can I change the slide?
Yeah. Finish. Yeah.
It is also very important to know that secondary is directional in nature, because it has we are going to also this determine geometry of complex, right? Geometry of complex, how many ligands are combining, that represents the geometry. If ligands are four, that means it will be either tetrahedral or a square planar. And if ligand is five, it will be trigonal bipyramidal. If ligand is six, it will be octahedral, like this. Are you getting
Yes.
my
Yes.
point?
Yeah. Yeah. Yeah.
Okay. And this is directional in nature because it determines the geometry, because there will be overlapping of orbitals which are directional in nature. There will be no overlapping of s orbital, which is non-directional, but there will be overlapping of d, which is directional.
Okay. Okay. Yeah.
Got it?
Yeah. Yeah.
Very. Can I change the slide?
Yes. Yeah.
Okay. So I am going to write a question, and the question is very easy. Uh, The correct stoichiometric stoichiometries order of the stoichiometries of AgCl formed when AgNO3 in excess is treated with the complexes COCl3 dot 6NH3, then COCl3 dot 5NH3, then COCl3 dot 4NH3 respectively. Yes, so I'm going to give you option as well, so that it
Okay.
will confuse you. So the option is 3 AgCl, 1 AgCl, 2 AgCl. Option B is 3 AgCl, 2 AgCl, 1 AgCl. Option 3 is 2 AgCl, 3 AgCl, 1 AgCl. Option D is 1 AgCl, 3 AgCl, 2 AgCl. Please do let me know.
Yeah, not getting.
Okay, it's very easy. See, correct order of stoichiometry of AgCl. You know that if AgNO3 gonna react with this 6NH3, can I write this as CONH3 whole 6 and Cl3? Can I write this?
Yeah.
As you know, cobalt can make 6 bond, not more than this. So what can I write this? Now, if you are going to react this with AgNO3, you know that this Ag and Cl can form precipitate. And how many? And this is in excess. And NO3
Okay.
has negative sign. So this all Cl3 will go with Ag and form 3 AgCl.
Yes.
Yes or
Yeah.
no? It can easily form, and this NO3 can satisfy the counter ions charge.
Yeah, yeah.
Now, again, the next one you are going to look at CO, NH3 whole 5, but it makes 6 bonds, 6 ligand it requires. So one of the Cl will come inside and two of the Cl go outside, right? Again, you are going to react this with AgNO3, which is in excess. So what it will be? It will be again 2AgCl because this is in excess and there is only Cl, 2Cl. So 2Ag will come here and form precipitate 2AgCl. Are you getting my point?
Yeah, 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 yeah.
And then again you can think of, right, the next one AgCl it will be, because this is 4NH3, that means CO NH3 whole 4, and as you can see 6 ligands required and we have only 3 Cl, so 2 Cl will come outside inside and 1 Cl will be outside. So if 1 Cl, so 1 Ag will combine to form 1 AgCl. So the answer will be, I think, this,
Okay,
right?
okay, okay.
Very good. Can I change the slide?
Wait, 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 1 minute. Uh,
Okay.
yeah, okay, done.
Okay. Then the last question, and in the next class we are going to do the P block of class 12.
Okay.
Cobalt 3 chloride forms several octahedral complexes. Right with ammonia. Yes, which of the following will not give test of chloride ions with silver nitrate AgNO3 at 25 degrees centigrade? I think you can do it easily. COCl3 4NH3. B option is COCl3 5NH3. C is COCl3 6NH3. D is COCl3 dot 3NH3. The strong ligand, first we will make it ligand and then go for the weak field ligand.
Yeah, yeah. Oh, yeah, I can sir solve this one. Not getting.
Okay, so see, if you are going to make a this as a complex, you can write CO NH3 whole 4 and then Cl2 and 1 Cl will come, and if you are going to react this with AgNO3, it will give AgCl. That means it will give test of chloride ions.
Okay, okay, yeah, okay,
If
sure.
you are going to ionize it, you will get Cl minus. That shows it is.
Yeah, test of
So
chloride. Yeah.
choose
Right.
one which does not ionize, which does not have Cl minus. If you are again going for this NH3 whole 5 1 Cl you are going to take, and 2Cl will be outside. That will give you
Yeah.
2Cl minus, and that is also ionized.
So
In
C
the same
option.
way,
Yeah.
no, NH3 whole 6, and it will give 3Cl minus.
Okay. Okay. Yeah. 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 So
And
D.
the
Yeah.
one which does not have any count